There's a comet out there that shouldn't exist, 3I-ATLAS. And now new information from the TESS satellite released on the 14th of October 2025 corroborates this. Using more than 9,000 images, the new findings lift the lid on what appears to have been a deliberate cover-up. And tonight, we lay this new evidence bare to settle this mystery once and for all. And away from the Atlas news, we explore a mysterious star that pulses every 44 minutes in radio and X-rays, and no one knows why. Could it be a new entrant to the mysterious cosmic objects category? We also shed light on 4 coronal mass ejections that are racing towards Earth and whose effects could be felt and seen this week. And finally, we look at the ghost particle, a neutrino so powerful it shattered every record, crashing into Earth with an energy once thought impossible. Stay with me until the end, because what we'll discover together will fundamentally change how you think about what's watching us from the dark. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as the stories unfold in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. Tess says, no tail. Why that breaks the simple comet story. Imagine a night sky filled with telescopes, each one worth millions, all pointed at the same target. Hundreds of instruments, from ground-based observatories to spacecraft floating in the silence of space, all tracking a single object as it races through our solar system. Now imagine that the most sensitive instrument of them all, after stacking over 9,000 individual images, says something nobody expected. It says there's no tail. On October 14th, 2025, astronomers released the results of a massive data analysis from TESS, the Transiting Exoplanet Survey satellite. They had taken more than 9,000 frames of 3I-ATLAS, an interstellar visitor that's been causing headaches since its discovery. They stacked those frames together, a technique called co-adding that's designed to pull faint signals out of the noise. When you stack images like this, you're essentially adding up all the light frame by frame until even the faintest whisper of structure becomes visible. It's like listening to a barely audible song and turning up the volume with each repetition until you can finally hear the lyrics. What Tess found, or rather didn't find, was extraordinary. The object appeared as a point source, a dot, no extended coma, no diffuse cloud of dust and gas spreading outward, no tail streaming away from the sun. When they measured the radial brightness profile, how the light falls off as you move away from the centre, it dropped like a star, not like a comet. Stars are point sources because they're so far away that even their enormous sizes collapse into a single pixel. Comets are supposed to be different. They're supposed to spread out, to show structure, to have that iconic tail that's been inspiring wonder and terror for millennia. The point spread function, or PSF, is the pattern of light you get from a point source after it passes through your telescope's optics. Every telescope has one, and it's like a fingerprint. When Tess looked at 3I-ATLAS, it saw only that fingerprint, nothing beyond it. The analysis team could quantify exactly what this meant. If there had been dust beyond a certain surface brightness, they would have seen it. The stacking process increases signal-to-noise ratio so dramatically that even faint features become detectable. They could derive constraints on dust density, particle size, and ejection velocity. All the numbers pointed to the same conclusion. Whatever dust might be there, it's not behaving the way comet dust should behave. Other observations tell a different story, though, and this is where things get strange. JWST, the James Webb Space Telescope, has detected water vapour and carbon dioxide around this object. Spectroscopic measurements show mass loss, volatiles escaping into space. These are signatures of activity, of a comet doing what comets do. But where's the tail? Where's the visible? Evidence of all that material streaming away? You're forced into a corner here. Either the coma is so compact, so unnaturally dense and confined, that it remains invisible to optical telescopes while still producing detectable gas signatures, or something else entirely is happening. It's like watching a campfire burn and seeing no smoke rise. Either the smoke is being compressed into invisibility by some mechanism we don't understand, or what we're calling a fire isn't really a fire at all. The contradiction sits there, unavoidable. Tess spent months staring at this object with one of the most sensitive instruments we've ever built for detecting faint extended structures. It saw nothing. But other instruments, tuned to different wavelengths, different physical processes, are screaming that something is definitely happening. One of these observations is missing something crucial, or our entire framework for understanding what a comet should look like is about to break. And here's what keeps me up at night. We've seen comets do strange things before, but we've never seen them do this. We've never had an object that so perfectly mimics a point source while simultaneously showing chemical signatures of vigorous activity. The numbers don't just fail to add up, they actively contradict each other. This isn't a minor discrepancy that can be explained by different observing conditions or instrumental quirks. This is a fundamental disagreement about what the object is doing. The test data is public now. Anyone can download it, run their own analysis, check the numbers. The results are reproducible. The no-tail finding is solid, which means we need to figure out what's happening, because if we can't explain this with conventional comet physics, we're going to have to start considering explanations that sound uncomfortably exotic. But before we get there, we need to understand just how deep these contradictions go, and why different instruments are painting completely different pictures of the same object. Part 2. Cross-instrument contradictions. JWST, ground arrays, spectrographs. Picture JWST, that $10 billion jewel of infrared astronomy, swiveling its mirrors toward 3I-ATLAS. The observations come back and they're clear. Carbon dioxide, water vapour, a gas coma rich in volatiles. The spectrographs are picking up molecular signatures, emission lines that tell us atoms are being excited, molecules are vibrating, gases flowing outward from the nucleus. Meanwhile, ground-based optical telescopes are seeing asymmetries, or in some cases seeing almost nothing at all. Different instruments, different stories. What gives? The answer lies partly in what each instrument is actually measuring. JWST operates in the infrared, looking at wavelengths where molecules emit light as they vibrate and rotate. It's incredibly sensitive to gas, to the chemical composition of whatever's floating around the nucleus. It doesn't need to see reflected sunlight to detect a coma. It's listening to the molecules singing in the infrared, and those songs are loud and clear. SphereX, another infrared mission, has reported large amounts of vaporized carbon dioxide around 3I-ATLAS, with carbon dioxide to water ratios that are unusual even by the standards of weird comets. Optical telescopes are different. They're looking at reflected sunlight, at how dust particles scatter the light of the sun back toward us. To see structure in an optical image, you need extended dust. You need particles spread out over space that can catch and redirect sunlight. If the dust is too compact, too close to the nucleus, or if the particles are the wrong size to efficiently scatter at optical wavelengths, you might not see much of anything even if gas is pouring off the object. This is where scattering functions come in. Small dust particles, micron-sized grains, scatter light efficiently and can form visible tails. Larger particles, millimetre to centimetre grains, don't scatter as well and they move more slowly. They're harder to kick away from the nucleus because they have more mass. These larger grains might hover close to the object, creating a compact but optically faint envelope that optical telescopes struggle to detect, but that still produces plenty of gas as ice sublimates from their surfaces. Then there's geometry, the phase angle, the angle between the sun, the object and the observer, changes how we see any tail or coma structure. If we're looking at the object from the wrong angle, a tail could be foreshortened, pointing almost directly toward or away from us, rendering it effectively invisible even if it exists. Different instruments observed at different times, from different positions in their orbits, seeing the object from different angles. A tail visible to one might be hidden from another purely by geometric bad luck. We've seen cross-instrument disagreements before. Comet Ison in 2013 was predicted to be spectacular, and then disintegrated, but different telescopes reported different levels of activity at different times. See 2017. K2 showed a coma in some observations and looked quiet in others, sparking debates about whether it was truly active or just venting gas intermittently. The difference here is scale. ATLAS isn't just showing variations, it's showing a binary split. Either tail or no tail, either point source or extended object. There's very little middle ground in the observations. The timing mismatches make it worse. JWST observed during certain windows, ground telescopes during others. TESS was staring continuously but at lower spatial resolution. What if the object is intermittently active, pulsing out dust and gas in bursts rather than steady streams? Then one telescope might catch it during an active phase, while another sees only quiescence. The observations would look contradictory even though both are accurately reporting what they saw at that moment. But even accounting for all these effects, the level of disagreement is unusual. Deep stacking of optical images from professional observatories should recover faint dust features if they're there. The fact that TESS, after stacking thousands of frames, sees nothing extended suggests either the dust is extraordinarily compact, or it's simply not there in the quantities we expect. And if it's not there, where's all that gas coming from? Gas doesn't just appear, it comes from ice sublimating off dust grains, or from the nucleus directly. Either process should produce dust as well. You start to wonder if you can trust any single instrument. Each one is seeing part of the elephant, reporting faithfully what its particular sensors detect. But the composite picture isn't coming together into anything coherent. This is where most astronomical mysteries get resolved. You gather more data, refine your models, realize you are missing some subtle effect like unexpected scattering properties or an unusual composition. But every time we add another observation of ATLAS, the picture gets murkier instead of clearer. And now we come to the spacecraft question, the observation that might actually resolve everything or make it infinitely worse. Because there's one instrument that might have had the perfect view, the perfect resolution, the perfect geometry to see what ATLAS really looks like up close. The Psyche mission was out there. Its trajectory might have brought it within viewing range, and if it captured images, where are they? Part 3. Timeline and the Psyche. Pivot. Where Psyche fits, and where the public record goes quiet. We've hit a wall with Earth-based and space-based telescopes all disagreeing about what they're seeing. Now we need to talk about what might be the most important observation that hasn't been discussed publicly. The Psyche spacecraft, launched by NASA to study the metal-rich asteroid 16 Psyche, has been travelling through interplanetary space with a suite of imaging instruments. Its mission is to reach its target asteroid, but along the way it's equipped with cameras that routinely capture calibration images, navigation frames, and opportunistic science observations. The spacecraft carries an imager capable of taking detailed photographs. During its cruise phase, mission teams regularly point these cameras at various targets to test systems, calibrate instruments, and gather bonus science when opportunities arise. This is standard procedure for interplanetary missions. You've got a camera, you're flying through space, you take pictures when you can. NASA has released some of these images publicly. Calibration shots of Earth and the Moon from various distances, star fields for navigation verification, that sort of thing. Here's where the timeline gets interesting. Based on the publicly available ephemeris data, the positions and trajectories of both Psyche and 3I-ATLAS, there are windows when the interstellar visitor would have been within potential viewing range of the spacecraft's cameras. Not close up necessarily, but close enough that a targeted observation might have captured useful data. The exact geometry depends on orbital mechanics that we can calculate from published mission parameters, but the possibility exists. So where are those images? NASA maintains archives of raw mission data. Most space missions eventually release their raw frames, or at least metadata about what was captured and when. These archives are how amateur astronomers sometimes discover comets or asteroids in old images, how researchers go back and find things that were missed during the initial analysis. The raw images from Psyche's instruments should be findable, either in NASA's planetary data system or in mission-specific archives. The mystery is that no public release of raw Psyche images showing 3I-ATLAS during closest approach periods has been announced. This could mean many things, and we need to be careful about jumping to conclusions. Let's walk through the benign explanations first, because they're perfectly plausible. Spacecraft data downlink is a constrained resource. Deep space missions can only send back so much data during each communication window with Earth. Mission planners prioritize what gets transmitted. Engineering telemetry comes first, then science data from the primary mission objectives, then everything else. If Psyche's cameras captured images of ATLAS, those frames might be sitting in the spacecraft's memory, scheduled for downlink during a future communication window when bandwidth is available. There's also compression and data management to consider. Spacecraft don't have unlimited storage. They use ring buffers that overwrite old data when new data comes in. If ATLAS images weren't flagged as high priority, they might have been compressed heavily, or even overwritten by later observations. This happens more often than the public realizes. Not every frame captured by a space mission makes it to Earth in full resolution. Metadata and indexing errors are another possibility. The images might exist in the archive but aren't properly catalogued. Wrong timestamps, mislabeled target fields, corrupted headers. Anyone who's worked with large astronomical databases knows how easily data can become effectively lost just by being filed in the wrong place or with the wrong keywords. An image of ATLAS might be sitting in the archive labelled as a calibration frame or a star field, waiting for someone to notice what's actually in it. Then there's the bureaucratic explanation. Space agencies have embargo periods, data rights policies, mission team exclusive access windows. It might simply be that the images exist, the mission team is analysing them, and they'll be released on a schedule that hasn't arrived yet. Science teams often get first crack at their data before public release. This protects the people who designed and built the instruments, giving them time to publish their findings before others scoop them using the same data. All of these explanations are reasonable. None of them require conspiracy or cover-up. They're just the normal friction of how space missions operate. But here's the thing. Absence of evidence is not evidence of absence. We don't know what was captured because we can't see the full archive. We don't know what was prioritised for downlink, what was compressed, what was labelled how. The metadata that would tell us might itself be incomplete or inaccessible. What we can do, what we should do, is ask. Freedom of Information Act requests can compel release of government-held data. Archive access requests can be filed. Mission logs, SLU logs, instrument activity reports. These are documents that exist and can be requested. The question is whether the images that might resolve the ATLAS mystery are sitting in an archive somewhere, waiting to be discovered, or whether they were never captured at all, or whether they were captured and are being held for reasons we don't yet understand. This is where the story could go in multiple directions. If the images exist and get released, we might finally see what ATLAS really looks like, resolving the contradictions between TESS and JWST and everything else. If they don't exist, we need to figure out why a spacecraft with working cameras didn't capture what might be the astronomical event of the decade. And if they exist but can't be accessed, then we have a different kind of problem entirely, one that raises questions about transparency and data governance in space science. Part 4. Physical alternatives to COMET, non-COMET hypotheses that fit the data. Let's step back from the archive question and ask something more fundamental. What if 3I-ATLAS isn't a comet in any normal sense? What if we've been trying to fit it into the wrong category from the start? If this object isn't following comet rules, what else could it be? And can any alternative explanation actually survive all the constraints we've piled up? Hypothesis 1. A large inert body with micro-outgassing. Imagine a chunk of rock and ice from another star system, shaped by different formation conditions than anything in our solar system. Maybe it's mostly inert, not actively sublimating like a comet, but still releasing small amounts of gas through cracks, through rare pockets of volatile ice exposed on its surface. This would explain the gas signatures JWST sees without requiring the massive dust production that would create a visible tail. The object stays compact, appears point-like, but still shows chemical activity. The problem with this model is quantifying the gas production rates. JWST's measurements suggest significant volatile loss. You can't hide that much gas production in microcracks without also kicking up dust. Ice doesn't sublimate cleanly. It drags dust particles with it as it vaporizes. You'd need a very specific composition, maybe pure volatile ices somehow separated from the dust, and that seems geologically implausible. Hypothesis 2. A fragment cloud. What if 3I-ATLAS isn't a single object but a tightly bound swarm of smaller fragments, all travelling together? Individually too small to resolve even with our best telescopes, but collectively producing the brightness we measure. Think of it like a school of fish or a flock of birds, where the group behaves as a unit. Each fragment produces a little gas, a little dust, but the material stays confined within the swarm rather than streaming away in a classic tail. This could explain the point-like appearance. If the fragments are close enough together, closer than our angular resolution can separate, we'd see them as a single object. the gas production would be distributed across many small surfaces rather than coming from one nucleus, potentially creating different scattering properties than we expect. But this model has problems too. Why would fragments stay bound together? They'd need some collective gravitational pull, or they'd drift apart over interstellar distances. And a swarm should show some structural variation, some elongation, or fuzziness, even if we can't resolve individuals. Hypothesis 3. Electrodynamic effects. This is where things get exotic. Suppose the dust particles around Atlas are electrically charged, and there's a magnetic field or electric field strong enough to hold them close to the nucleus. Charged dust can levitate, can be trapped in configurations that don't follow simple ballistic trajectories. We see this in planetary rings, in laboratory plasma experiments, in regions where electromagnetic forces dominate over gravity. If Atlas is carrying a charge, if it's generating fields through some process we don't understand, the dust might not escape into a tail at all. It might hover, circulate, remain confined. The gas would still escape because molecules are harder to trap electromagnetically, but the dust would stay put, invisible to optical telescopes looking for extended structure. This would explain almost everything. Compact appearance, gas detection, no visible tail. The catch is that we have no mechanism for how an inert body generates the necessary fields. You'd need something active, something generating energy. And that brings us to hypothesis 4, the one that makes scientists uncomfortable, but that we have to at least put on the table given how strange everything is. What if this object is artificial? What if it's engineered, carrying active systems, producing the signatures we're measuring through technological rather than geological processes? An artificial object could explain the contradictions perfectly. Active reflectors could produce the brightness variations. Energy sources could generate gas emissions without requiring ice sublimation. The compact appearance would be natural for a manufactured structure. The electromagnetic signatures, if we found them, would be expected rather than mysterious. The problem, of course, is that this is an extraordinary claim requiring extraordinary evidence, and we don't have that evidence yet. We have anomalies, contradictions, unexplained observations, but those aren't proof. Each of these models makes predictions. The micro-outgassing hypothesis predicts we should eventually see some dust production, faint but detectable if we stack enough observations. The fragment cloud model predicts structural variations over time as the swarm evolves. The electromagnetic model predicts we should find field signatures, polarization anomalies, maybe radio emissions. The artificial model predicts things that don't occur naturally, geometric structures, spectral lines from industrial processes, temporal patterns that suggest control rather than chaos. What's remarkable is that none of these models is a perfect fit. Each explains some observations while creating new questions about others. The natural explanations require unlikely compositions or configurations. The exotic natural explanations require physics we haven't observed in comets before, and the artificial explanation requires us to accept that we're looking at technology from another civilization, which is a leap that most scientists won't make without overwhelming proof. But we're going to need one of these explanations, or something even stranger, because the standard comet model is broken. We can't keep saying it's a comet while it refuses to act like one. At some point, if an object consistently violates your expectations, you have to update your model of what the object is. We might be at that point with Atlas. Part 5. Formalizing the challenge. What would convincingly prove non-natural? Let's draw a line in the sand. Let's establish exactly what would need to be shown to break the natural explanation, and force us to seriously consider that we're looking at something artificial. This isn't about speculation anymore. This is about defining testable criteria that would satisfy even skeptical scientists. First criterion, resolved structure inconsistent with known physics. If we could take an image of Atlas with resolution high enough to see its shape, and that shape showed sharp edges, right angles, symmetric patterns, or moving parts, that would be significant. Natural objects are lumpy, irregular, shaped by accretion and collisions and gravitational forces that don't produce geometric precision. A spherical object isn't suspicious. Spheres minimize surface energy. But a cube, a cylinder, articulated components that move relative to each other, those would demand explanation. Second criterion, unambiguous spectral lines from compounds that don't belong. Comets show water, carbon dioxide, carbon monoxide, organic molecules. All things we expect from primordial ices. If spectroscopy revealed technetium, which only exists as a product of nuclear reactions, or if we saw industrial compounds, synthetic polymers, isotope ratios that don't occur naturally, that would be a red flag. The universe makes a limited palette of chemicals through stellar nucleosynthesis and chemistry. Anything outside that palette needs accounting for. Third criterion, multiband registration anomalies. Take images in different wavelength bands and overlay them. Natural objects show predictable patterns. Hot regions emit more infrared. Dust scatters optical light. Gas emits at specific wavelengths. If the images in different bands don't align the way physics says they should, if there's structure in one band that doesn't correspond to anything in others, that suggests something more complex than simple thermal and scattering processes. Fourth criterion, metadata and telemetry signatures. This is about data provenance. If spacecraft observations exist, the raw frames should have headers with timestamps, instrument settings, checksums, calibration data. These headers can be verified, cross-checked against mission logs. Inconsistencies here could indicate tampering, but more importantly, the presence of consistent, verifiable metadata strengthens any claim about what was observed. You can't prove something extraordinary with data you can't authenticate. Fifth criterion, correlated signals across different physical domains. If ATLAS showed simultaneous optical brightening, radio bursts, X-ray flashes and neutrino detections, all time locked to the same events, that would be remarkable. Natural processes can produce multi-wavelength emission, but the correlations follow patterns we understand. Blazars, pulsars, supernovae, these have characteristic signatures. Something completely novel in its multi-wavelength behaviour would demand a new explanation. History gives us examples of how data quality and provenance can make or break extraordinary claims. The Apollo program's data tapes were nearly lost, requiring restoration efforts decades later. Some were recorded over, some degraded. Astronomical archives have had their own issues. Mislabeled data, degraded storage media, institutional knowledge lost when key people retired. The quality of evidence matters as much as the evidence itself. There's also the sociology of it. Mission teams face enormous pressure. Careers depend on successful missions, on publishable results, on not making claims they can't defend. National interests play a role. Some data might be classified or embargoed for strategic reasons that have nothing to do with scientific merit. The fear of ridicule is real. No scientist wants to be the person who claimed aliens and was wrong. The professional cost is too high. So what would a credible dataset look like? Raw, uncompressed frames, not processed or enhanced. Complete metadata headers that can be verified against independent sources. Checksums that prove the data hasn't been altered. Multiple independent observations from different instruments that corroborate each other. Open access so that anyone can analyse the data and attempt to reproduce the findings, and ideally a chain of custody that's documented from capture through storage to release. Any video, any claim, any announcement about ATLAS should be held to these standards. If someone says they have spacecraft images showing something extraordinary, the first question should be, where are the raw frames? Can we verify the metadata? Can independent analysts access the data? Without that level of transparency, we're just looking at another ambiguous observation that raises more questions than it answers. The burden of proof for an extraordinary claim is enormous, and it should be. Science has progressed by being rigorous about evidence, by demanding reproducibility, by not accepting claims just because they're exciting. But science has also progressed by following anomalies, by taking seriously the observations that don't fit, by being willing to update models when data demands it. We're at a moment where the ATLAS observations are strange enough to warrant serious attention but not yet clear enough to draw firm conclusions. What happens next depends on whether we can get access to the decisive observations, whether new data closes the gaps in our understanding or widens them, and whether the scientific community can balance healthy skepticism with genuine curiosity. The framework is there. The criteria are defined. Now we wait to see if the evidence emerges. Part 6. ASCAP J1832, a 44-minute heartbeat in radio and X-rays. Let's zoom out from ATLAS for a moment and look at something happening in our own galaxy that's forcing astronomers to question what they thought they knew about cosmic objects. Astronomers using the Australian Square Kilometre Array Pathfinder and NASA's Chandra X-ray Observatory have discovered an object called ASCAP J 1832-0911. It pulses like a heartbeat every 44 minutes in both radio waves and X-rays simultaneously. The discovery came as part of a survey looking for transient radio sources, objects that appear and disappear or vary in brightness over time. Long-period transients, or LPTs, are a relatively new category of astronomical objects that flash in radio wavelengths every tens of minutes to hours. They're rare, poorly understood, and don't fit neatly into any existing classification. ASCAP J 1832 is the first one observed to pulse in X-rays as well as radio, which makes it uniquely strange. The data is precise. The object emits a 2-minute burst of radio waves, then goes quiet for 42 minutes, then bursts again. The cycle repeats with clockwork regularity. Chandra observations show X-ray pulses synchronized with the radio bursts, not perfectly overlapping but definitely correlated. The object is localized to roughly 15,000 light-years away, somewhere in our galaxy, but not in any obvious stellar association or nebula. What could produce such a signal? The immediate suspects are all magnetically active objects. Magnetiers are neutron stars with insanely powerful magnetic fields, and they're known to pulse. But magnetar pulses are usually much faster, milliseconds to seconds, not 44 minutes. You'd need some novel configuration, some reason for the field to store energy slowly and release it periodically, and nobody has a convincing model for that yet. Ultra-magnetized white dwarfs are another possibility. These are dead stellar cores that have collapsed down to roughly Earth size, but still rotate and maintain strong magnetic fields. If you had a white dwarf spinning with a 44-minute period, which is unusually slow, and if it had active accretion or magnetic reconnection events synchronized to its rotation, you might get periodic pulses. But again, the timing is weird. Most white dwarfs either spin much faster or have lost their magnetic fields entirely. Binary systems offer another explanation. If you had two objects orbiting each other with a 44-minute period and some interaction between them, maybe accretion or tidal heating, produced periodic flares that could explain the observations. The problem is that a 44-minute orbital period implies the objects are very close together, close enough that they should either have merged already or be spiraling in rapidly due to gravitational wave emission. None of the standard models are satisfying. Each requires tweaking parameters, invoking special conditions, explaining away inconvenient observations, and this is before we try to connect it to ATLAS, which seems impossible on the surface. ASCAP J 1832 is a galactic object, probably stellar in nature, pulsing in radio and X-rays. ATLAS is an interstellar visitor, showing optical and infrared anomalies but no confirmed radio or X-ray detections. They're completely different types of phenomena in completely different contexts. But here's why I'm bringing it up. If one object in our galaxy can break all the existing patterns, can produce a signal that doesn't match any known class of astronomical object, then we should be humble about declaring what is and isn't possible for other weird objects we encounter. ASCAP J 1832 is proof that the universe still has tricks we haven't catalogued, mechanisms we don't understand, classes of objects we haven't discovered yet. The discovery also highlights how much we miss. ASCAP is a relatively new radio telescope array, only operational for a few years. Chandra has been up since 1999, but can only observe what we pointed at. ASCAP J 1832 has probably been pulsing for thousands or millions of years, and we only just noticed. How many other strange objects are out there, detectable with current technology but not yet found because we haven't looked in the right place or the right way? This is relevant to ATLAS because it changes the prior probabilities. Before ASCAP J 1832, you might have said, weird periodic signals in multiple bands aren't a thing natural objects do, so any claim of such signals is probably instrumental error or misinterpretation. Now we know such signals exist, and we have no good explanation for them. That should make us more cautious about dismissing anomalies in other objects just because they don't fit existing models. It also suggests a research strategy. When you find one anomaly, you should look for others and see if patterns emerge. Maybe there's a connection, maybe there isn't, but you won't know unless you look. Which brings us to the question, could ATLAS and ASCAP J 1832 possibly be related by some common physics? It sounds absurd, but let's at least explore it before dismissing it. Part 7. Crosslinks. Are ASCAP J 1832 and ATLAS related in any plausible physics? We need to be clear up front. There is no proof that ASCAP J1832 and 3I-ATLAS are related in any way. They're different types of objects, different scales, different contexts. What we're doing here is exploring analogies, looking for potential shared mechanisms, asking whether the same exotic physics could operate in different regimes. Even if the answer is no, the exercise of thinking through it illuminates what tests we should be performing. Start with energy scales. ASCAP J1832 is producing radio and X-ray pulses. Radio emission can come from synchrotron radiation, where charged particles spiral in magnetic fields, or from coherent plasma processes. X-rays require higher energies: hot plasma, magnetic reconnection, particle acceleration to relativistic speeds. These are energetic processes, far more energetic than anything we associate with comets, which are just ice and rock heated by the sun. But what if ATLAS is carrying or generating magnetic fields? Comets do have induced magnetospheres when solar wind interacts with their ionized comas. The interaction is weak, nothing like the organized fields in magnetos or accretion systems, but it exists. If ATLAS had an unusually strong internal field, or if it was carrying charged particles that created field structures, could those fields produce radio emission under the right conditions? Plasma physics gives us some possibilities. Coherent radio emission can come from plasma instabilities, from regions where the density of charged particles varies sharply, from boundary layers where different plasmas interact. If ATLAS is venting gas, that gas gets ionized by solar UV. An ionized coma is a plasma, and plasmas can support waves, instabilities, emission mechanisms. Most of the time these are too weak to detect, but under special conditions, maybe extreme charge densities or unusual magnetic configurations, you might get detectable signals. The timing is completely different though. ASCAP J1832 pulses every 44 minutes with precise regularity. That regularity suggests rotation, orbital motion, or some kind of resonant oscillation. ATLAS doesn't show that kind of periodicity in its optical observations. If there's periodic behaviour, it's on different timescales, days or weeks rather than minutes. So any shared mechanism would have to operate across a huge range of characteristic times, which seems unlikely unless there's a common underlying process that scales differently in different environments. What about X-rays? X-ray emission from comets has been detected before, produced when solar wind ions charge exchange with neutral atoms in the coma. It's faint, requires sensitive instruments to detect, but it's real. If ATLAS has an unusually dense or active coma, X-ray emission wouldn't be surprising. The question is whether that emission would be periodic, structured, synchronized with anything else we're observing. Natural charge exchange is pretty uniform, not pulsed. Let's consider a unified speculative hypothesis, just as a thought experiment. Suppose there's a class of objects, natural or otherwise, that maintain strong localized magnetic fields and dense plasma environments. In a galactic context, with stellar mass scales and compact objects, you get ASCAP J1832, regular pulses from rotation or oscillation, radio and X-ray emission from plasma processes. In the interstellar context, with a much smaller object like ATLAS, the same field and plasma physics operates but manifests as confined comas, unusual gas-to-dust ratios, maybe radio bursts too faint or brief to have been detected yet. This hypothesis makes testable predictions. If ATLAS and ASCAP J1832 share underlying physics, we should look for faint radio pulses from ATLAS, especially during perihelion when solar wind interaction is strongest. X-ray flashes correlated with optical brightening or gas production events. Polarization signatures in ATLAS's scattered light that indicate organized magnetic fields. Faraday rotation of background radio sources seen through ATLAS coma, which would reveal magnetic field strength. Neutrino detections correlated with either object if acceleration mechanisms are producing high-energy particles. Most of these observations haven't been done or reported. Radio telescopes haven't been systematically monitoring ATLAS at high-time resolution. X-ray observatories might not have been pointed at it during active phases. The data to confirm or rule out the connection might simply not exist yet. The comparison is useful even if the answer is negative. If we observe ATLAS at radio wavelengths during its next active period and see nothing, that constrains models. It tells us there's no coherent plasma emission, no synchrotron radiation, no radio-producing mechanism operating. That's valuable information. It eliminates hypotheses, and if we do find radio pulses or X-ray correlations or any of the signatures we're predicting, that would be extraordinary. It would suggest ATLAS is doing something far outside the normal behaviour of comets, something that connects it to active stellar objects like ASCAP J1832. That would push us firmly into exotic territory, where conventional explanations no longer hold, and we have to start seriously considering alternatives we'd rather not contemplate. The point is to be systematic. Anomalies in one object inform how we think about anomalies in another. Patterns emerge when you compare across different phenomena, and sometimes the wildest seeming connections turn out to have truth to them because nature uses the same physics in different contexts. We won't know until we look. Part 8. The 220 PeVy ghost particle. Why a single neutrino matters. A single particle changed everything. On a day that should have been unremarkable, deep beneath the Mediterranean Sea, an array of detectors called KM3-NET recorded something that shouldn't exist according to our comfortable understanding of cosmic ray physics. A neutrino with an energy of 220 peta-electron volts slammed through the detector, leaving a trail of light that told a story about the most violent processes in the universe. Let me explain what that means, because numbers at this scale lose their intuitive weight. A peta-electron volt is 1,000,000 billion electron volts. The protons in the Large Hadron Collider, the most powerful particle accelerator humans have ever built, reach energies of about 14 trillion electron volts. This neutrino was carrying 16,000 times more energy than those protons. It's a cosmic bullet fired by something so powerful we don't have a complete theory for how it works. Neutrinos are ghost particles. They pass through normal matter as if it isn't there. Right now, billions of neutrinos from the Sun are streaming through your body, through the Earth, continuing into space without interacting with a single atom. They have almost no mass, no electric charge, no properties that would let them bump into ordinary matter. Detecting them requires enormous volumes of transparent material, ice or water, instrumented with sensors that watch for the rare occasions when a neutrino does interact, producing a charged particle that emits light as it travels faster than light can travel in that medium. KMthNet operates in the Mediterranean, using the sea itself as the detector volume. Arrays of light sensors hang on cables, monitoring cubic kilometers of water for the telltale flash of Cherenkov radiation that signals a neutrino interaction. The ARCA component detected this particular event, saw the characteristic pattern of a muon track, worked backward through the physics to determine that the neutrino must have had at least 220 peta-electron volts of energy. The analysis has been confirmed. This isn't a glitch or a misidentification. It's real. Why does this matter? Because neutrinos at these energies point to cosmic accelerators operating at scales we barely understand. The most powerful candidates are blazars, supermassive black holes at the centres of galaxies that are actively feeding, launching jets of plasma at nearly the speed of light. Those jets can accelerate protons to enormous energies, and when those protons collide with ambient photons or matter, they produce pions that decay into neutrinos. Gamma-ray bursts, the death screams of massive stars collapsing into black holes, are another possibility. Anything that can accelerate particles to these energies is operating at the extremes of physics. Now here's the connection, tenuous but worth exploring. Could 3I-ATLAS be embedded in, passing through, or somehow connected to a high-energy astrophysical environment? The object came from interstellar space. We know its rough trajectory, can trace it back into the galaxy, but we don't know what it encountered on its journey. Did it pass through a supernova remnant, near a pulsar wind nebula, through regions of space where magnetic fields or plasma densities create particle acceleration zones? The speculation goes further. If ATLAS is carrying exotic matter, fields we don't understand, or has properties we haven't detected, could it interact with the solar wind or interplanetary medium in ways that produce high-energy particles? Could it seed neutrino production through mechanisms that don't operate in normal comets? This sounds absurd until you remember that we don't actually know what ATLAS is. We're calling it a comet because it's in our solar system and shows some volatile activity, but everything about it is anomalous. A concrete test exists. Neutrino detectors like KM3-NET, IceCube at the South Pole, and others maintain continuous monitoring. Their data is time-stamped and direction resolved. If a burst of high-energy neutrinos occurred, coincident with ATLAS's perihelion passage, or with its active phases, or with any unusual behaviour we've observed optically or spectroscopically, that correlation would be significant. The chances of a random coincidence are calculable. If the correlation is strong enough, it suggests a physical connection. This has been done before with other astrophysical phenomena. When IceCube detected neutrinos from the direction of a known blazar during an active phase, it confirmed that blazars are indeed neutrino sources. The multi-messenger astronomy revolution relies on correlating signals across different types of particles and radiation: light, neutrinos, gravitational waves. Each messenger tells you something different about the source because each is produced by different physics and travels through space differently. Neutrinos are special because they're so hard to stop. If ATLAS is producing them, they'd escape directly, carrying information about whatever process is generating them. Gamma rays might be absorbed by dust or gas, radio waves might be scattered, but neutrinos punch through everything and arrive at Earth pointing back toward their source. They're the ultimate cosmic messenger for seeing into environments that are otherwise opaque. The 220 peta-electron volt detection is proof that such messengers are out there, that we're living in a universe with processes violent and powerful enough to produce them. It's a reminder that our census of cosmic phenomena is incomplete. We don't know all the ways nature can accelerate particles, generate fields, produce high-energy radiation. New classes of objects, new mechanisms, are still being discovered. So when we look at ATLAS with all its contradictions and anomalies, we should keep in mind that the universe has already shown us it can do things we didn't predict. ASCUP J, 1832 pulses in ways no model fully explains. A neutrino with unimaginable energy came from somewhere. Black holes merge and produce gravitational waves we only learned to detect a decade ago. The inventory of cosmic weirdness keeps growing. Maybe ATLAS is just a comet with unusual composition and we're overthinking it. But maybe it's another entry in the catalogue of things we didn't expect, another phenomenon that will require new physics or new categories to explain. The only way to find out is to keep observing, keep correlating, keep asking whether different anomalies might be connected. And to do that effectively, we need access to all the data, including the observations that might be sitting in archives waiting to be analysed. Part 9. Space Weather Overlay. 4 CMEs, aurora forecasts, and why environment matters. While we've been focused on distant objects and exotic particles, something much closer to home has been making life complicated for observers. The Sun has been active, dramatically so. 4 coronal mass ejections launched toward Earth in quick succession, expected to arrive October 15th through 17th, 2025. These are billion-ton clouds of magnetized plasma ejected from the Sun's corona, travelling through space at millions of kilometers per hour. And when they hit Earth's magnetic field, they cause geomagnetic storms. For aurora watchers, this is exciting news. Geomagnetic storms drive charged particles into Earth's upper atmosphere near the poles, where they collide with atmospheric gases and produce the shimmering curtains of light we call aurora. The stronger the storm, the farther from the poles the aurora can be seen. These 4 CMEs have prompted forecasts of major aurora displays potentially visible at mid-latitudes. For astronomers trying to observe faint objects like 3I-ATLAS, space weather is a nightmare. The same charged particles that create beautiful aurora also create noise. Radio observations get contaminated by ionospheric scintillation, where fluctuations in the ionized upper atmosphere cause signals to shimmer and fade like stars twinkling but worse. Cosmic ray showers increase, hitting detectors with spurious signals. Optical observations can be affected by air glow, where excited atmospheric molecules emit light that adds background noise to images. Spacecraft instruments face direct effects. Solar energetic particles can cause bit flips in electronics, corrupting data or triggering false detections. Star trackers used for spacecraft attitude control can be confused by high-energy particles hitting their sensors, creating false stars. Camera sensors can show noise spikes, hot pixels, streaks from cosmic ray hits. All of this has to be filtered out during data processing, and sometimes the filtering isn't perfect. Here's where it gets insidious. Space weather creates plausible deniability for data problems. If frames are missing from an archive, if images show unexpected artifacts, if telemetry has gaps, you can always blame the space weather. A CME hit during that observation window. Solar energetic particle event corrupted the data. The spacecraft had to safe mode because of the storm. All of these are legitimate effects that really do happen. But they're also convenient excuses. How do you distinguish between genuine space weather impacts and other reasons data might be incomplete or problematic? You look at the details. Space weather effects leave specific signatures. Cosmic ray hits appear as sharp spikes in single pixels or small clusters. Ionospheric scintillation shows characteristic timescales and frequency dependencies. Spacecraft safe modes generate specific telemetry patterns and log entries. If you have access to the full metadata, you can usually tell what happened. The problem is when you don't have access. If all you're told is data was lost due to space weather, without seeing the detailed logs, the instrument diagnostics, the before and after calibration frames, you can't verify the claim. It might be true. It might be a simplification of a more complex situation, or it might be covering something else entirely. This isn't paranoia. This is how data integrity works. Scientific claims require verifiable evidence, and evidence requires provenance. You need to know where data came from, how it was processed, what happened to it along the way. When gaps appear in that chain of custody, when explanations are vague or incomplete, the data becomes less reliable for making strong claims, whether those claims are mundane or extraordinary. Historical examples abound. The Hubble Space Telescope's NICMOS instrument had a cooling system failure that was initially blamed on generic thermal issues, but turned out to involve specific mechanical problems that took years to fully diagnose. Mars Observer was lost during orbital insertion with telemetry, suggesting a fuel line rupture, but the incomplete data left room for alternative theories. When data is incomplete, explanations remain ambiguous. For ATLAS observations, this matters because we're relying on a patchwork of instruments, each with their own vulnerability to environmental effects. Ground telescopes fighting through atmospheric turbulence and weather, space telescopes dealing with radiation and thermal cycles, radio arrays coping with ionospheric conditions. If all of these instruments are showing slightly different results, how much is due to genuine physical differences in what they're observing versus instrumental and environmental effects? The 4 CMEs arriving this week add another layer of complication. Any observations during this window will have to account for enhanced backgrounds, possible instrumental effects, increased uncertainty in calibration. This doesn't make the observations worthless, but it does mean the error bars get bigger, and bigger error bars mean more ambiguity about what's really happening with ATLAS. There's also a timing question that nags at me. If decisive spacecraft observations of ATLAS exist, if there are frames that would resolve the contradictions we've been discussing, why haven't they been released during a week when space weather provides a ready-made explanation for any delays or data issues? It would be the perfect time to say, we wanted to release earlier, but the CMEs complicated our data processing. Here's what we have. The absence of such an announcement is notable, though not necessarily significant. Space weather is part of the structural blindness we face when trying to understand cosmic phenomena. The environment between us and the object, between the instrument and the data archive, between observation and publication, introduces noise, gaps, uncertainties. Some of this is unavoidable physics, some of it is technological limitations, and some of it might be institutional or procedural, the way data gets handled and released by organizations with their own priorities and constraints. To get past this blindness, we need redundancy. Multiple instruments, multiple observing strategies, multiple independent analyses of the same data. We need transparency about what's being observed when, about data quality flags, about processing pipelines. And we need a culture where asking questions about data provenance isn't seen as adversarial, but as essential to doing good science. Part 10. Instruments, Biases, and the Archive. How we're structurally blind. Let's talk about what happens to an observation between the moment photons hit a detector and the moment you can access the resulting data. This pipeline, unglamorous and technical, determines what we can actually know about the universe, and it's full of places where information can be lost, corrupted, or simply never make it to public view. Start at the detector. A photon arrives, deposits its energy, creates a signal. That signal gets converted to a digital value, a number representing brightness, at a specific pixel, at a specific time. Already you've lost information. The conversion has noise, quantization error, sensitivity variations across the detector. Cosmic rays and charged particles hit the sensor constantly, creating false signals that have to be identified and removed. Hot pixels, dead pixels, column defects all create patterns in the data that aren't astrophysical. Next comes compression. Raw detector frames are enormous. A single, high-resolution image might be hundreds of megabytes. A spacecraft can generate thousands of frames during an observation campaign. There isn't enough bandwidth to send all that data to Earth uncompressed, so it gets compressed. Sometimes lossless compression that preserves all the information, sometimes lossy compression that throws away details deemed less important. The choice of what to compress and how much affects what science can be extracted later. Then there's the ring buffer problem. Spacecraft have finite memory. They can't store everything forever. Data gets written to memory, held there until it can be downlinked, then often overwritten by new data. If something interesting happens but isn't flagged as high priority, if the observation window closes before the data is transmitted, those frames might never make it to Earth. They're gone, overwritten, irretrievable. Downlink scheduling is another choke point. Deep Space Network time is precious. Every spacecraft, every mission competes for communication windows. When a spacecraft does get to transmit, it sends what mission control has prioritized. Engineering telemetry first, to make sure the spacecraft is healthy. Then primary science data. Then secondary science, calibration frames, bonus observations, in whatever order the mission team has decided. If your object of interest is considered low priority, its data might wait weeks or months for downlink. Once data reaches Earth, it enters the archive pipeline. This involves more processing. Raw frames get converted to standard formats. Headers are populated with metadata: target coordinates, observation time, exposure duration, filter settings, quality flags. This metadata is critical because it's how you search the archive later. Mislabeled metadata means data becomes effectively lost, even though it physically exists in storage. Archives get reorganized, migrated to new storage systems, re-indexed as software evolves. Each migration is an opportunity for errors. File corruption, checksum mismatches, broken links between data and metadata. Large archives with millions or billions of files are almost guaranteed to have some fraction that are damaged, mislabeled, or inaccessible due to technical glitches. Then there are embargo periods and proprietary data rights. Mission teams often get exclusive access to their data for months or years before public release. This protects the scientists who built the instruments and designed the observations, giving them time to analyze and publish, before others scoop their results. It's a reasonable policy, but it means potentially interesting data might be sitting in restricted archives, known to a small group, not available to the broader community for independent verification. Bureaucratic delays compound these issues. Releasing data requires resources. Someone has to prepare the files, write documentation, verify quality, set up access systems. Space agencies and observatories are often understaffed and overworked. Data release schedules slip. Low-priority observations might languish in internal archives simply because nobody has time to process and release them properly. There are historical examples of important data being recovered from archives years after collection. Reanalysis of Hubble archival images has discovered objects missed in the original processing. Voyager tapes were found in storage decades later, preserving observations that had been thought lost. Amateur astronomers have found comets and asteroids in publicly released images that professionals overlooked. The archive is vast, and no one can examine every frame of every observation systematically. This structural blindness affects all of astronomy, not just ATLAS. We're only seeing the subset of the universe that gets observed, that gets successfully downlinked, that gets properly archived and labelled, that gets analysed by someone with the interest and resources to do so. The true universe is filtered through this pipeline, and we don't know what we're missing. For ATLAS specifically, this means several things. First, the contradictions between instruments might partially reflect these pipeline effects. TESS sees no extended coma because its data processing is optimized for stellar photometry, not extended sources. Ground telescopes might miss faint tails because their reduction pipelines assume point sources. JWST sees gas because its spectrographs are exquisitely sensitive to molecular emission, but it doesn't do wide-field imaging that would reveal dust structure. Second, the absence of Psyche images in public archives could be explained by any of dozens of pipeline failures or delays, none of which require conspiracy or cover-up. But explaining the absence doesn't make it less frustrating. If observations exist, they should be accessible for analysis. If they don't exist, we should know why observation windows were missed. Transparency about the process is as important as the data itself. Third, this suggests a research strategy for anyone trying to understand ATLAS or similar anomalies. Don't just look at published results or official releases. Dig into the archives directly. Download raw frames if available and reprocess them with different assumptions. Look for metadata inconsistencies that might indicate mislabeled observations. Check observation logs against actual archived data to find discrepancies. File access requests and FOIAs to push institutions toward greater openness. Citizen science has a role here. Amateur astronomers and data scientists who aren't constrained by institutional pressures or career concerns can ask questions and pursue analyses that professionals might avoid. They can collaborate across communities, sharing data and methods. The history of astronomy includes many important contributions from amateurs, and the digital age makes that kind of participation easier than ever. The structural blindness is real, but it's not insurmountable. It requires persistence, technical skill, and a willingness to navigate bureaucracy. It requires building coalitions of people who care enough about getting answers to do the unglamorous work of data archaeology. And it requires maintaining pressure on institutions to improve their data pipelines, their release schedules, their transparency, because ultimately the data exists. Photons hit detectors, signals were recorded, bits are stored somewhere. The question is whether we can access them, verify them, and analyze them openly. That's a question of policy and priority as much as it is of physics. Part 11. The data hunt. Specific, immediate forensic actions to perform now. We can't just speculate and wait for someone else to provide answers. Here's exactly what needs to be done, step by step, to hunt down the data that could resolve the ATLAS mystery. This is a roadmap for anyone with the determination to pursue it. First, determine the precise observation windows. We need to calculate the exact UTC timestamps when 3I-ATLAS would have been within Psyche spacecraft's potential field of view. This requires ephemeris data for both objects, which is publicly available from JPL Horizons and other sources. The Horizons system provides precise position and velocity data for solar system objects at any requested time, accounting for gravitational perturbations and observation geometry. Calculate angular separations, visibility windows, favourable geometries. This means determining when ATLAS and Psyche were both positioned such that the spacecraft's instruments could have observed the object. Consider factors like sun angle, which affects both illumination and whether sensitive detectors can be pointed in certain directions without risk. Account for spacecraft attitude constraints and operational modes during different mission phases. Identify the specific dates and times when Psyche's cameras could have been pointed at ATLAS, either deliberately or as part of routine monitoring. Spacecraft often conduct optical navigation images, calibration sequences, or engineering tests that sweep across fields of sky. ATLAS might have appeared in such observations even if it wasn't the intended target. The window analysis should span the period from Psyche's launch through present day, with particular attention to times when ATLAS was bright or at favourable viewing geometries. Second, identify instrument specifications and data products. Psyche carries specific cameras with known fields of view, sensitivities and operating modes. These specifications are published in mission documentation, typically in instrument papers, mission design documents, and technical reports available through NASA's Technical Report Server or mission websites. The spacecraft's imager specifications include pixel scale, spectral response, readout noise characteristics, and typical exposure parameters. Determine what those instruments can detect, at what limiting magnitudes, with what exposure times. This requires calculating the expected brightness of ATLAS at different times, factoring in its distance from both the Sun and Psyche, its phase angle, and any activity that might enhance or reduce visibility. Compare these predictions against the camera's documented sensitivity limits. Calculate whether ATLAS would have been bright enough and close enough to produce a useful image. This establishes whether an observation was feasible, not just geometrically possible. A faint object in a wide field might be detectable with long exposures, but invisible in short engineering frames. Conversely, a bright object might saturate detectors if exposure times weren't adjusted. Understanding these technical constraints tells us what kind of data to expect and what might have been missed. Third, search existing archives. Systematically. NASA's planetary data system hosts data from planetary missions. The archive structure is standardized but not always intuitive, with data organized by mission, instrument, and observation time using specific naming conventions that vary between missions. The PDS uses hierarchical directory structures, where understanding the organizational logic is essential for effective searching. Search by instrument name, by observation date ranges covering the windows identified earlier, by target coordinates. Download available image indices and metadata catalogs. These indices contain summary information about each observation without requiring download of full image files, making systematic searches computationally feasible. Use automated scripts to search for file names, headers, or annotations that mention ATLAS, interstellar objects, calibration targets, or even generic field observations that happen to include the right coordinates. Python libraries like Astropy and Planetary Data Reader can parse PDS formats and automate searches across thousands of files. Regular expressions can match various naming schemes that might reference the object. The archive search should be exhaustive. Don't just look for obvious matches. Check engineering data products, calibration frames, and rejected observations that might have been excluded from primary science archives. Sometimes the most interesting data hides in supplementary collections or data marked as poor quality. Fourth, file formal data requests. If archive searches come up empty, submit Freedom of Information Act requests for specific observations. Be precise. Request. All raw image frames from Psyche's cameras during the calculated observation windows, along with accompanying metadata, instrument logs, and data quality assessments. Specificity matters in FOIA requests. Vague requests get vague responses or delays while agencies seek clarification. FOIA requests have to be responded to, though the response might be delayed or claim exemptions. Common exemptions include national security, proprietary information, or data that hasn't completed standard processing. Even a refusal provides information about whether data exists and why it's not being released. The response timeline and type of exemption claimed can be revealing. Consider also international data request mechanisms if collaborating institutions outside the US are involved. European Space Agency, JAXA, and other space agencies have their own data policies and request procedures. Coordination across multiple agencies might be necessary if ATLAS observations involved international partners. Fifth, cross-match with mission logs. Spacecraft operations generate extensive logs. Attitude control data showing where the spacecraft was pointing. Power logs showing when instruments were active. Communication logs showing when data was downlinked. These engineering records provide a detailed reconstruction of spacecraft state and activity at any given time. Some of this telemetry is archived and can be requested. Mission operations centers maintain comprehensive logs for troubleshooting and mission reconstruction purposes. While detailed telemetry might not be in public archives, it exists and can be requested through appropriate channels. If the logs show the camera was on and pointed at ATLAS's coordinates, but no images appear in the archive, that's a discrepancy worth investigating further. Such gaps might indicate data loss during transmission, storage failures, or processing decisions that excluded certain observations from archival. Each explanation has different implications and suggests different follow-up actions. Sixth, inspect checksums and version histories. Digital files have checksums, hash values that verify data integrity. Archives should maintain these along with version histories showing when files were added, modified, or replaced. These metadata are crucial for ensuring data hasn't been corrupted or tampered with, and reputable archives maintain detailed provenance information. Request checksum logs for relevant time periods. Look for gaps, anomalies, files that show modification dates after initial archival. This can reveal whether data was altered, deleted, or had problems that required reprocessing. Legitimate reprocessing happens routinely as calibration improves or errors are discovered, but the history should be documented and transparent. Compare checksums against multiple mirrors if the data is distributed across different archive sites. Discrepancies between mirrors suggest problems with data integrity or synchronization. Cross-reference file timestamps with mission event logs to verify whether file modification dates align with documented reprocessing activities. Seventh, reprocess available public frames. Even if specific ATLAS frames aren't identified, download and analyze all Psyche images from relevant time periods. modern image processing can extract information that automated pipelines miss, stack them, look for faint sources, check whether Atlas might be visible in background fields, even if it wasn't the primary target. Apply modern detection algorithms, machine learning-based source finders, anything that might reveal a faint object that automated pipelines missed. Convolutional neural networks trained on asteroid and comet images can identify faint moving sources against star fields. Difference imaging that subtracts template star fields can highlight transient or moving objects. Examine metadata carefully. Sometimes objects appear in images but aren't catalogued because they weren't bright enough to trigger automated detection thresholds, or because their motion made them appear as artifacts. Human examination of candidate detections can identify real objects that automated systems rejected as noise or cosmic ray hits. Eighth, form a citizen audit coalition. This is too much work for one person. Organise a collaborative effort bringing together amateur astronomers, data scientists, planetary scientists willing to contribute expertise, legal advocates who understand 4IA processes, and programmers who can build tools for archive mining. Distribute tasks, share findings, maintain transparency about methods and results. Use collaborative platforms like GitHub for code sharing, Slack or Discord for coordination, and cloud storage for data distribution. Establish clear documentation standards so everyone's work can be verified and built upon by others. The amateur astronomy community has proven remarkably capable in similar projects. Discovery of transiting exoplanets, classification of galaxies, and monitoring of variable stars have all benefited from citizen science efforts. The combination of distributed effort and varied expertise often catches things that individual researchers miss. Ninth, consider whistleblower channels. If data exists but is being improperly withheld, insiders might know. Establish secure communication channels for potential whistleblowers to share information anonymously. This has to be done carefully, with strong verification to prevent hoaxes, but genuine leaks have revealed important information in past scientific controversies. Use encrypted communication tools, establish verification protocols to assess credibility, and protect source anonymity rigorously. Whistleblower protection requires both technical security and operational discipline to prevent inadvertent identification through metadata or behavioral patterns. Be prepared for false leads. Anonymous channels attract both genuine information and deliberate disinformation. Verification is essential. Any claims must be cross-checked against verifiable facts, and extraordinary claims require extraordinary evidence before being taken seriously or disseminated publicly. 10th, parallel the forensic hunt with public pressure. Write to observatory directors, mission principal investigators, funding agency heads, petition for open data policies, for faster release schedules, for better archive accessibility. Scientific institutions respond to stakeholder interest, and demonstrating that the community cares about these questions can influence prioritization decisions. Use social media, science journalism, public forums to raise awareness. Sometimes institutional inertia responds to public interest when internal advocacy hasn't succeeded. Popular interest can motivate agencies to allocate resources to data archaeology that might otherwise remain buried in archives awaiting eventual processing. Engage with science communicators who can translate technical issues into compelling narratives. The story of hunting for hidden observations of a mysterious object has inherent interest beyond the specialist community. Broader attention can generate resources and support that purely internal advocacy cannot. This isn't a quick process. It requires patience, technical skill, and resilience in the face of bureaucratic obstacles, but it's feasible. Every step is concrete, uses existing tools and procedures, and has precedent in other data archaeology efforts. The question is whether enough people care enough to invest the time and effort. The payoff could be enormous. If Psyche images of Atlas exist and can be recovered, they might settle the question definitively. High-resolution views of the object's morphology, its structure, whether it has a tail or doesn't, whether it shows geometric features or appears natural. That data, if it exists, is the key to moving from speculation to knowledge. And if the data doesn't exist, if the forensic hunt comes up empty, that's valuable information too. It tells us observation windows were missed, priorities were set differently than we might have hoped, opportunities weren't seized. That informs how we plan future observations, how we advocate for different mission priorities, how we think about what gets observed and what doesn't. The hunt starts now. The tools exist. The methods are clear. What's needed is the will to pursue it and the community to support the effort. Because answers don't come from waiting. They come from digging. Part 12. Experimental tests. What new observations would kill or confirm alternate models? Even if we never find the psyche images, we're not helpless. There are observations we can still do, tests that would discriminate between the competing hypotheses about what ATLAS really is. Let me lay out the decisive experiments, what they would measure, and what results would force us to abandon or accept each model. Test 1. High-resolution polarimetry at multiple phase angles. Polarization measures how light's electric field oscillates, and different materials polarize light differently. This fundamental property of electromagnetic radiation provides a powerful diagnostic tool for understanding surface composition and structure without ever touching the object in question. Dust particles scatter sunlight with predictable polarization patterns that depend on particle size, composition, and shape. The physics is well understood. When unpolarized sunlight hits a particle, the scattered light becomes partially polarized, with the degree and orientation of polarization revealing information about the scatterer. Metallic or crystalline surfaces produce different polarization signatures than fluffy aggregates. Smooth faces reflect differently than rough textures. Ice crystals have their own distinctive patterns. By observing ATLAS at different angles between the Sun, object, and Earth, what astronomers call phase angles, and measuring how polarization changes across that geometry, we can infer surface properties with remarkable precision. The phase angle matters because scattering behavior depends on viewing geometry. Forward scattering, back scattering, and side scattering each produce characteristic polarization curves. If the polarization signature matches typical comet dust, that supports the natural hypothesis. Cometary dust has been studied for decades, and we know what to expect. Certain trends with phase angle, particular degrees of linear polarization, specific wavelength dependencies. If it shows patterns consistent with metal, ice crystals, or geometric structures, that's anomalous. Artificial surfaces might show unusually high polarization, or geometric patterns inconsistent with random particle distributions. The required instruments exist. Polarimeters on large ground telescopes, maybe HST if observation time can be secured. The technology is mature. What's needed is dedicated observation time and careful calibration to achieve the precision necessary for distinguishing subtle differences in polarization behavior. Test 2. Narrowband imaging during dormant phases. Most gas imaging of ATLAS has been done near perihelion when solar heating drives activity. That's natural. Objects are brightest when closest to the Sun, and that's when most observational resources get allocated. But this focus on perihelion means we've potentially missed crucial evidence about what powers ATLAS's activity. Observe it farther from the Sun using narrowband filters that isolate specific molecular emission lines. Carbon monoxide, carbon dioxide, water. These filters, typically just a few nanometers wide, block out continuum light and reveal emission from specific molecular transitions. If the object is a normal comet, emission should drop dramatically when it's far from the Sun and cold. The relationship between heliocentric distance and activity is well established for comets. Beyond about 3 AU, most water emission ceases. CO persists farther out, but even it eventually fades. If emission continues when it shouldn't, if gas production remains significant without solar heating to drive it, that demands explanation. Natural processes like stored heat or radioactive decay might account for some residual activity, but there are limits to how much. A comet's interior can retain heat, and certain isotopes produce warmth, but not enough to sustain major gas production at large distances. Significant activity beyond 5 AU, for instance, would be extraordinary and would require either exotic composition or an internal energy source beyond what solar heating provides. The observation campaign should span multiple orbits, tracking ATLAS from perihelion out to aphelion and back. Document when activity starts, when it peaks, when it ends. Compare the activity curve with solar distance. Any deviations from expected patterns provide clues about internal structure and energy sources. Test 3. Deep stacking with adaptive optics or space telescopes. Get the highest resolution images possible. Stack dozens or hundreds of exposures to maximize sensitivity to faint structures. Image stacking is a proven technique. By combining many exposures, random noise averages away while real signal accumulates. Features invisible in single frames emerge in deep stacks. Use adaptive optics on giant ground telescopes like Keck or VLT to overcome atmospheric blurring. These systems measure atmospheric turbulence in real time and deform flexible mirrors to compensate, achieving near diffraction limited resolution. Request JWST or HST time for imaging, not just spectroscopy. Space telescopes avoid atmospheric distortion entirely and can reach wavelengths blocked by Earth's atmosphere. If ATLAS has any extended structure, any hint of asymmetry or geometric features, deep high-resolution imaging will reveal it. A completely symmetric point source would be unusual. Natural objects have irregularities, even if subtle. Cometary nuclei are lumpy, asteroid surfaces are cratered, and even nominally symmetric objects show brightness variations across their surfaces. Look for jets, fans, shells, the typical structures active comets display. Look also for geometric patterns, straight edges, regular shapes. Image at multiple wavelengths to separate dust continuum from gas emission. Create color maps showing compositional variations. Use difference imaging, subtracting images taken at different times to highlight changes. The resolution requirements are demanding. We need to resolve features at the scale of the nucleus itself, perhaps down to tens or hundreds of meters if possible. That requires either space telescopes or the largest ground instruments with excellent adaptive optic systems operating under ideal conditions. Test 4. Coordinated multi-wavelength monitoring. Organize a campaign involving radio telescopes, X-ray satellites, optical instruments, all observing ATLAS simultaneously during an active period. This requires coordination across facilities, advanced planning, and willingness from time allocation committees to support what is essentially a fishing expedition. The goal is to catch correlations. If optical brightening coincides with radio pulses, that suggests electromagnetic activity beyond simple thermal radiation. If X-ray flashes align with gas ejections seen spectroscopically, that implies specific plasma processes generating high-energy photons. If everything varies independently, that's consistent with chaotic natural activity, where different processes operate on different timescales for unrelated reasons. But synchronized behavior across unrelated wavelengths would be extraordinary, requiring organized energy release mechanisms. Natural chaotic processes don't typically show tight correlations across vastly different wavelengths unless there's a common triggering mechanism or organized energy conversion process. The observational cadence matters. Some phenomena happen on timescales of minutes or hours, requiring continuous monitoring. Others unfold over days or weeks. The campaign needs sufficient temporal coverage to catch transient events, while maintaining long-term continuity to establish baseline behavior. Test 5. Neutrino and cosmic ray coincidence monitoring. This is harder because it requires luck and access to neutrino detector data streams. Neutrinos are notoriously difficult to detect, requiring massive detectors deep underground or under ice. Most cosmic neutrinos pass through Earth without interaction. Detection rates are low, and most detections are background events from Earth's atmosphere or distant astrophysical sources. But petition KM3Net, IceCube, and other facilities to flag any neutrino detections coincident with ATLAS observation windows. These detectors log every event with precise timing. Searching their databases for coincidences is computationally straightforward once access is granted. Check cosmic ray detector networks for any excess events when ATLAS is active. Arrays like the Pierre Auger Observatory and Telescope Array continuously monitor for high-energy cosmic rays. The probability of random coincidence is calculable. Given detection rates and observation windows, we can determine how many coincidences we'd expect by pure chance. A statistically significant correlation would be shocking and would immediately elevate ATLAS to a high-energy astrophysical phenomenon. Comets don't emit detectable neutrinos or cosmic rays. If ATLAS does, it's operating physics beyond standard cometary processes. The sensitivity is limited. Unless ATLAS produces substantial neutrino or cosmic ray flux, we won't detect anything. But the potential payoff, definitive evidence of high-energy particle acceleration, justifies the effort, especially since searching existing detector databases requires minimal resources. Test 6. rotation, and light curve. Analysis. Comets and asteroids rotate, and their brightness varies as different parts of their surface face the Sun and observer. This fundamental fact of solar system dynamics provides another diagnostic tool. Detailed light curve analysis can reveal rotation periods, axis orientations, sometimes even rough-shaped models. If ATLAS shows regular periodic variations, the period and amplitude tell us about its shape and spin. Short periods suggest a small, cohesive body. Long periods might indicate a large object or tidal locking to some external influence. Large amplitude variations suggest an elongated or irregular shape. Small variations suggest a more spherical body or a viewing geometry where we're looking down the rotation axis. If the light curve is unusually stable, too smooth, lacking the irregularities natural tumbling bodies show, that would be anomalous. Real asteroids and comet nuclei have surface features, bright and dark patches, topographic relief, that produce light curve irregularities. A perfectly smooth light curve suggests either a remarkably uniform surface or active compensation for natural variations. If variations correlate with other activity indicators in ways that suggest control rather than inertia, that would be remarkable. For instance, if gas emission pulses always occur at specific rotation phases, that suggests localized vents positioned deliberately. If brightness changes lead or lag rotation phases in ways inconsistent with passive solar heating, that implies active processes modulating output. The observation program requires sustained monitoring over complete rotation periods, which might span hours to days. Automated telescopes and photometric monitoring networks can provide continuous coverage. Multiple sites at different longitudes ensure 24-hour coverage. The data analysis is well established, with standard techniques for period finding and light curve inversion. Test 7. Magnetic field detection via Faraday rotation. Radio waves passing through magnetized plasma experience Faraday rotation, where the polarization angle twists proportional to field strength and plasma density. This effect, predicted by classical electromagnetism and observed in many astrophysical contexts, provides a direct probe of magnetic fields. If ATLAS has a magnetic field and an ionized coma, background radio sources seen through that coma should show rotation. The geometry requires alignment. ATLAS must pass in front of or near a bright radio source as viewed from Earth. These events are rare but predictable using orbital calculations and radio source catalogues. This is technically challenging, requiring precise polarization measurements of radio sources along the line of sight at multiple times. The measurements must be accurate to degrees or fractions of degrees in polarization angle. Ionospheric Faraday rotation must be calibrated out since Earth's ionosphere also rotates polarization. But it's doable with VLBI networks and could directly detect fields that shouldn't exist around a natural comet. Comets don't have intrinsic magnetic fields. Their nuclei are too small and non-metallic. Any field detection would be extraordinary. It might indicate metallic composition, internal dynamos, or electromagnetic systems operating beyond natural processes. The field strength and structure would constrain models of what's generating it. Each test makes predictions under different models. If ATLAS is a natural comet with unusual composition, we expect comet-like polarization, activity only when solar heated, irregular shape and rotation, no multi-wavelength correlations, no magnetic field signatures. If it's a fragment swarm, we expect slightly unusual polarization from collective scattering, extended but compact structure, chaotic light curves, no organized electromagnetic behavior. If it's electromagnetically active through natural but exotic processes, we expect anomalous polarization, magnetic field detection, multi-wavelength correlations, activity possibly even when far from Sun. If it's artificial, all bets are off, but we might see geometric structures, organized behavior, emissions that don't match natural spectra, temporal patterns suggesting control. The key is that these tests are falsifiable. We can state in advance what results would support or contradict each hypothesis. That's how science works. You make predictions, you test them, you update your beliefs based on results. What we can't do is continue with observations that are ambiguous, that can be interpreted multiple ways depending on your prior assumptions. We need observations designed to break tie votes, to force conclusions, to eliminate possibilities. That requires coordinated effort, telescope time allocation prioritizing these questions, and willingness from observatories to invest resources in what might seem like a long-shot investigation. But the scientific payoff is enormous. Either we confirm ATLAS is a weird comet and learn something new about cometary physics, or we discover it's something else entirely and open a new field of study. The observation windows are coming. ATLAS will have future perihelion passages, future active phases, future opportunities. The question is whether the astronomical community will seize them, or whether ATLAS will remain an ambiguous footnote in the catalogue of interstellar visitors. Part 13. If it were artificial, consequences for SETI, policy, and scientific procedure. Let's confront the implications directly. If we accept, even hypothetically, that 3I-ATLAS might not be natural, everything changes. The frameworks we use for searching for extraterrestrial intelligence, the policies governing how we handle such discoveries, the procedures for validating extraordinary claims, all would need immediate revision. Start with SETI protocols. Traditional SETI searches for radio signals, beacons intentionally transmitted by technological civilizations trying to make contact. The assumptions are that communication is deliberate, uses electromagnetic radiation at specific frequencies, and originates from planetary systems around other stars. But if technological artifacts can travel between stars, if they can be small enough and numerous enough that we encounter them in our own solar system, the search space transforms completely. An artifact wouldn't necessarily broadcast. It might be dormant, observing passively, or operating on principles we don't recognize as communication. Detection would come from anomalous behavior, from physical properties inconsistent with natural processes, not from decoded messages. This shifts SETI from radio astronomy toward optical surveys, spectroscopy, astrometry, anything that can identify anomalous objects among the millions of natural bodies we track. The detection thresholds change too. Traditional SETI sets a high bar for claiming artificial signals, because the consequences of false positives are severe professionally and socially. But if artifacts might be physically present and observable, the burden of proof shifts. We can potentially examine them directly, get multiple lines of evidence, perform tests that radio signals don't permit. The standard becomes, does this object's behaviour, across all observational modalities, better fit artificial than natural models? Policy questions become urgent. Who owns the data if an artifact is confirmed? Currently, space agencies maintain control over their mission data, but discovery of non-human technology might trigger different jurisdictions. National security agencies might claim authority. International bodies like the UN Committee on the Peaceful Uses of Outer Space might assert responsibility. Legal frameworks for handling such discoveries don't really exist in actionable form. Scientific disclosure protocols are even murkier. The International Academy of Astronautics has SETI principles that outline how to handle detection of artificial signals, emphasizing international notification and scientific verification before public announcement. But these are voluntary guidelines, not enforceable regulations, and they were written assuming radio detections, not physical artifacts. If a spacecraft captured images of something artificial, who decides when and how that information gets released? Chain of custody for data becomes critical. Any claim of detecting artificial technology will face extreme skepticism, as it should. The only way to overcome that skepticism is with data whose integrity is unquestionable. Raw frames with headers signed cryptographically. Multiple independent observations cross-verifying the same phenomenon. Open archives where anyone can attempt to reproduce the analysis. Transparent methodology documenting every processing step. Anything less invites accusations of error, fraud, or misinterpretation. International coordination would be necessary but difficult. Different nations have different interests in space, different levels of transparency, different relationships between their space agencies and military establishments. An artifact detected by one nation's spacecraft might be considered a strategic asset rather than scientific data to be shared openly. Balancing scientific principles of openness against national security concerns would require negotiations at the highest levels. Historical analogies are limited. The discovery of pulsars in 1967 briefly raised speculation about artificial signals before the Lighthouse model explained them as rotating neutron stars. The WOW signal in 1977 remains unexplained but hasn't been reproduced. Neither case required the kind of policy response an actual artifact would demand. The closest parallel might be how the discovery of DNA structure or nuclear fission required international scientific cooperation and policy development, though even those don't capture the full scope. Ethical questions multiply. If an artifact exists, does it belong to whoever finds it, to humanity collectively, to whoever sent it? Do we have the right to study it, interfere with it, attempt communication? What if it's observing us? What if disturbing it triggers responses we can't predict? Science fiction has explored these scenarios, but they're not just fiction if we're actually facing the situation. There's also the risk of premature announcement. Claiming artificial technology based on insufficient evidence would damage credibility, possibly set back serious SETI efforts, and invite ridicule that makes future claims harder to evaluate fairly. But sitting on evidence while demanding ever higher confidence thresholds could also be irresponsible if the phenomenon is real and important. Finding the right balance requires judgment that's hard to encode in procedures, and we have to consider the public reaction. How would revelation of non-human technology affect society? Some would be thrilled, seeing it as humanity's greatest discovery. Others might panic, fearing invasion or existential threat. Still others would be skeptical regardless of evidence, seeing conspiracy or hoax. Managing the social impact while maintaining scientific integrity would be perhaps the hardest challenge. What's clear is that our current frameworks are inadequate. If Atlas or any other object turns out to be artificial, we're not prepared institutionally, procedurally, or culturally. That doesn't mean we shouldn't look, shouldn't investigate, shouldn't follow the data wherever it leads. It means we should be developing the protocols now before we need them, so that if the extraordinary becomes real, we have structures in place to handle it responsibly. The scientific procedure would be iterative. Observation, hypothesis formation, prediction, testing, revision. The same method that's worked for every other scientific question. The difference is stakes and scrutiny. Every step would be examined by critics looking for errors. Every claim would need to withstand the most rigorous skepticism. That's appropriate. Extraordinary claims require extraordinary evidence, and the process of gathering and validating that evidence needs to be beyond reproach. But we shouldn't let the difficulty paralyze us. The questions are askable. The observations are doable. The data, if it exists, can be found and analysed. What's required is courage to pursue anomalies seriously, rigour to avoid false conclusions, and transparency to maintain credibility. The framework exists. We just need to apply it consistently, even when the implications make us uncomfortable. The reality is that we're already in the process, whether we acknowledge it or not. Every observation of Atlas, every analysis of its properties, every attempt to explain its behaviour is part of the investigation. We're just not treating it with the systematic intensity it might deserve. The question is whether we'll continue with scattered, uncoordinated observations that leave ambiguities unresolved, or whether we'll mount a focused campaign designed to get definitive answers. If Atlas is artificial, we'll eventually know. Technology leaves signatures that can't be hidden indefinitely. Structure, composition, behaviour patterns, all would eventually reveal themselves with sufficient observation. The only question is how long it takes and how much opportunity we waste through hesitation or disorganisation. And if it's not artificial, proving that conclusively is also valuable, because it means we've learnt something new about the range of natural phenomena the universe can produce. Either way, the investigation itself pushes science forward. It forces us to refine detection methods, improve data handling, develop better models, and confront the question of how we would recognise intelligence if we encountered it in an unexpected context. Those are questions worth asking regardless of what Atlas turns out to be. Part 14. Broader cosmic pattern. Are we in a new era of big weirds? Step back and look at the bigger picture. We have 3I-ATLAS behaving unlike any comet we've seen before. We have ASCAP J 1832 pulsing in radio and X-rays with 44-minute regularity that doesn't match any known class of object. We have a 220 peta-electron-volt neutrino pointing to particle acceleration we can't fully explain. Are these isolated anomalies, or are we entering an era where the universe reveals itself to be stranger than we thought? Consider what's changed in the last decade. Survey telescopes like the Zwicky Transient Facility, Pan Stars, and the Vera Rubin Observatory scan enormous swaths of sky repeatedly, detecting anything that varies or moves. Radio arrays like ASCAP and Meerkat monitor the sky continuously, finding transient events that earlier instruments would have missed entirely. Neutrino. Detectors have grown from small experimental setups to cubic kilometre instruments. Gravitational wave observatories have opened an entirely new window on the universe. Every new capability reveals phenomena we didn't know existed. Fast radio bursts weren't discovered until 2007, not because they're rare, but because we weren't looking in the right way. Now we detect dozens per day and still don't fully understand what produces them. Neutron star mergers were theoretical until we detected one in 2017 through gravitational waves and electromagnetic radiation simultaneously. The universe keeps surprising us precisely because we're finally looking at it with sufficient sensitivity and coverage. Machine learning and artificial intelligence are accelerating this process. Algorithms can now scan through millions of images, spectra, light curves, finding patterns and anomalies that would take humans years to identify manually. This means we're discovering outliers faster than we can explain them. The catalogue of unexplained phenomena grows faster than the catalogue of understood ones. But there's a paradox here. More data means more noise. More surveys mean more statistical flukes. More instrumental artifacts misidentified as real signals. More false positives. When you're looking at billions of objects, 1 in a million events happen thousands of times. How do you distinguish genuine new physics from statistical outliers that inevitably occur in large data sets? The answer is correlation and replication. If weirdness clusters in certain types of objects, certain spatial regions, certain time periods that suggest something real, if anomalies are scattered randomly, appearing once and never reproducing, they're probably noise. ATLAS is weird, but it's one object. ASCAP J 1832 is weird, but it's one object. The neutrino is one event. Are they connected? Are there others we're missing? Or are we pattern matching on insufficient data, seeing connections that don't exist? Recent discoveries outside these examples hint at the scope. Astronomers have found exoplanets with atmospheres that shouldn't be stable, with orbital configurations that formation models struggle to explain, with densities that require exotic compositions. There are stars that dim irregularly like Tabby's star, generating speculation about megastructures before dust clouds prove to be the explanation. There are galaxies without dark matter, or with too much dark matter, defying our understanding of galaxy formation. In 2025, we're also seeing AI-assisted discoveries in astrophysics accelerate. Neural networks are finding gravitational lenses, identifying unusual spectra, predicting stellar evolution with accuracy that exceeds traditional models. But AI finds what it's trained to find. If the training data doesn't include artifacts or genuinely novel phenomena, the algorithms might overlook them or classify them as noise. We're becoming dependent on tools that could systematically blind us to the truly unexpected. The philosophical question underneath all this is whether we're revealing genuine strangeness or manufacturing it through observer bias. The universe has always been strange. We're just now seeing it clearly enough to recognize that strangeness. Or perhaps strangeness is relative, defined by how far observations deviate from our models, and as our models improve, they'll absorb what currently seems anomalous. I lean toward the former. The universe is under no obligation to conform to human intuition or 19th century physics. Quantum mechanics is strange. General relativity is strange. Dark matter and dark energy are profoundly strange. Each generation of physicists discovers that reality operates on principles that seem bizarre until you understand them. And even then they never quite stop being bizarre. So maybe we are in a strangeness era. Maybe the 21st century is when we finally have the tools to see the universe as it really is. Full of extreme conditions, exotic processes, scales and energies that push physical laws to their limits. ATLAS and ASCAP J 1832 and ultra-high energy neutrinos might be the first hints of a much larger catalogue of cosmic weirdness waiting to be discovered. Or maybe we're overthinking outliers, seeing patterns in randomness, letting our imaginations run ahead of our data. The only way to know is to keep observing, keep testing, keep subjecting our wild hypotheses to the harsh discipline of measurement. Science advances by taking seriously things that might be wrong, but investigating them carefully enough to find out. What's certain is that we're living through a remarkable time in astronomy. More discoveries are happening faster than ever before. The questions are getting deeper, and the answers more surprising. Whether ATLAS specifically represents something genuinely anomalous or just unusual, The fact that we can study an interstellar visitor in detail, debate what it means, and devise tests to probe its nature represents a capability that would have seemed like science fiction a generation ago, and there are more interstellar objects coming. Borisov and Oumuamua preceded ATLAS. Statistical models suggest dozens pass through the inner solar system every year, most too faint to detect. The Vera Rubin Observatory, when it reaches full operation, will find them by the hundreds. Each one is a messenger from another star system, carrying information about conditions and processes in environments we can't visit directly. Each one is an opportunity to test our assumptions and possibly discover we were wrong about things we thought we understood. The strangeness might just be getting started, and that's thrilling, even if it's also unsettling, because it means the universe still has secrets, still has surprises, still has the power to overturn our comfortable certainties and force us to think harder about what's possible. Part 15. Final synthesis. What we actually know, what we should demand, and the 3 tests that will settle this. Let's bring this back to Earth and summarise what we actually know for certain, separate speculation from fact, and define the path forward. Here's what we know. Tests stacked over 9,000 frames of 3I-ATLAS and found no extended coma, seeing it as a point source. This is solid, reproducible data. JWST and other infrared instruments have detected gas emissions, carbon dioxide and water vapour, indicating volatile activity. These observations are also solid. Ground-based optical telescopes have reported varied results, some seeing asymmetries, others seeing little structure. The observations are real, but inconsistent. Spacecraft observations from Psyche that might resolve these contradictions have not been publicly released, and we don't know definitively whether they exist. Here's what remains ambiguous. The physical mechanism producing gas without an obvious dust tail. The composition and structure of the object's nucleus. Whether the contradictions between instruments reflect genuinely anomalous behaviour or just observational selection effects and processing differences. Whether electromagnetic or plasma processes are playing any unusual role. Whether any of the multi-wavelength phenomena we've discussed, ASCAP J1832 and high-energy neutrinos, have any connection to ATLAS. Here's what is pure speculation, that ATLAS might be artificial or technological in nature, that Psyche spacecraft data is being withheld for non-scientific reasons, that there's a pattern connecting different cosmic anomalies through shared exotic physics. These ideas are worth exploring, worth testing, but they're not supported by conclusive evidence yet. They're hypotheses, not facts. Now, the verdict ladder. How do we move from natural to exotic, natural to artificial? What evidence pushes us from one rung to the next? Natural is the default. It requires only that we find some plausible combination of composition, structure, and environmental conditions that explains the observations without invoking new physics. Exotic natural requires that we identify processes operating in ATLAS that don't occur in typical comets, but are still consistent with known physics, perhaps electromagnetic effects or unusual ice chemistry. Artificial requires multiple independent lines of evidence showing behaviour inconsistent with any natural process, structure indicating design, and provenance of data that rules out error or contamination. The 3 critical tests that will settle this. Test 1. Archival forensic recovery. Get access to Psyche spacecraft data or any other spacecraft observations during ATLAS observation windows. Verify whether images exist, examine them for structure and morphology, authenticate their metadata and processing history. This is the most direct test because high-resolution images would show the object's actual appearance, resolving whether it's a typical irregular nucleus, a fragment cluster, or something geometric. The technical barriers are low, the institutional barriers might be high. But it's achievable through persistence and formal requests. Test 2. Decisive multi-wavelength coordinated observation. Organise a campaign during ATLAS's next active period with polarimetry across optical and infrared, spectroscopy monitoring gas production, radio telescopes searching for emissions, X-ray observatories watching for flashes, and particle detectors monitoring for coincident high-energy events. This comprehensive approach would capture correlations that single-instrument observations miss. It would test whether ATLAS shows electromagnetic activity, whether its behaviour is periodic or chaotic, whether it produces any signatures beyond what comets should. Test 3. High-energy event correlation. Continuously monitor neutrino detectors, cosmic ray networks, and gamma-ray observatories for any statistically significant correlation with ATLAS activity. This tests the most extreme hypothesis that ATLAS is connected to high-energy astrophysical processes. It's a long shot, but the data exists in real-time streams that can be analysed. If correlation appears, it transforms our understanding of what the object is. If correlation is absent, it eliminates a category of exotic explanations. Here's the 90-day roadmap. Days 1 through 30. Organise the Citizen Audit Coalition, divide up archival search tasks, file FOIA requests for Psyche data, and mission logs. Begin systematic downloading and reprocessing of available images from all missions that might have captured ATLAS. Days 30 through 60. Compile results from archival search. Prepare telescope proposals for coordinated observation campaign during next ATLAS active period. Reach out to neutrino detector collaborations requesting correlation analysis. Begin public advocacy campaign for data transparency. Days 60 through 90. Submit proposals, follow up on FOIA responses, publish preliminary findings from archival analysis. Establish communication channels with professional astronomers willing to contribute expertise and telescope time. Engagement strategy for anyone watching this. If you have data science skills, volunteer to help search archives and develop analysis tools. If you have access to telescopes, even small amateur instruments, contribute observations during coordinated campaigns. If you have legal expertise, assist with FOIA processes and data access requests. If you have platforms or audiences, raise awareness and pressure institutions for transparency. If you have funding, consider supporting citizen science efforts with grants or crowdfunding. Every contribution accelerates the timeline from mystery to answer. The emotional core of this story is that we're standing at a threshold. We have an object behaving strangely, enough to demand explanation, technology capable of getting that explanation, and a choice about whether to pursue it seriously or let it remain ambiguous. The easy path is to call it a weird comet and move on. The harder path is to acknowledge we don't understand it yet and commit to finding out why. Science progresses through exactly this kind of moment. When observations don't fit, when the standard model creaks under the weight of anomalies, you have to decide whether to patch it with ad hoc explanations or to consider that something fundamental might be wrong. Most of the time, the patches work and the standard model survives refined and strengthened. But occasionally, rarely, the anomalies are telling you something deeper, something that requires rethinking basic assumptions. We don't know which kind of moment this is yet. ATLAS might be a comet with unusual but ultimately explicable properties. Or it might be the first clear example of something we haven't categorized yet, natural but exotic. Or, in the scenario that sounds like fiction but can't be dismissed without evidence, it might be the first detected artifact from beyond our solar system. The probability of that last option is low, but low is not zero, and the implications are too significant to ignore just because they're uncomfortable. What we do know is this: the mystery is open, the tools are available, the tests are defined. We don't yet have proof of the impossible, but we have the strongest clues we've ever had about something that doesn't fit our understanding. The data exists somewhere, in archives or in instruments pointing at the sky right now. The question is whether we have the collective will to pursue it, the rigour to do it right, and the courage to accept whatever answers emerge. This is how discovery happens, not through sudden revelation, but through accumulated anomalies that force questions, investigations that follow those questions wherever they lead, and communities that collaborate to turn observations into understanding. The ATLAS mystery invites us into that process, offers us a role in figuring out what's real and what's misinterpretation. So let's go test it. Let's demand the data, perform the observations, do the analysis, and see what the universe is actually telling us. Because the only thing worse than discovering we are wrong about something fundamental would be having the opportunity to discover that and choosing not to look. The frontier is open, the mystery awaits, and somewhere in the data we haven't seen yet, or in observations we haven't made yet, the answer is waiting to be found.